the next speaker. He's Tom Roser, and he's going to give his talk on Zoom.
Okay, well, hello everybody, and I wish I could be there, but thank you very much for inviting me to give a talk at Willy's Memorial Symposium. So I'm going to talk about accelerating polarized proton beams. I was asked for ion beams, but all we do is proton beams in RIC, as well as a short part of my talk will be on the parity violation experiment that Willy participated at PSI, or SIN as it was called at the time, in Switzerland. So first, acceleration of polarized beams. So progress in accelerator technology is always motivated by and has been driven by advances in particle and nuclear physics. And it started from the very beginning with Ernest Lawrence's cyclotron and continues, of course, until today. You see the pictures of the cyclotron as well as the RIC rings at Brookhaven. And the exploration of spin in nuclei and nucleons required the development of polarized sources, and as we heard in several talks already, and the acceleration of polarized beams. Just a couple slides on some fundamentals of the acceleration of polarized beams of spin dynamics. It's all governed by the motion of a particle, charged particle with spin is governed by a precession equation, usually expressed in the laboratory frame. That goes back to Thomas and also Barkman, Michel, Intellecti. And the precession equation has several components. There is a precession with respect to a transverse magnetic field of the spin and one with respect to the longitudinal. And that's measured with regard to the velocity direction. And if you compare it with the Lorentz force, which is also a precession equation, then you can see that the coefficients are quite different for the transverse field. And there is no precession around the longitudinal field for the velocity. So from this, we can easily find that for a pure vertical field, so only the first term applies, the spin rotates g gamma times faster than the motion. And g here is the anomalous magnetic moment, or gyromagnetic ratio, really, which is about 2.8 for protons, and gamma, of course, is energy over mass. And so this number of rotations per turn is also called the spin tune. So spin tune is g times gamma, which means it increases with energy. If we want to manipulate the spin independent of the orbit, then at low energy, we can just simply use longitudinal fields like a solenoid. At high energy, we can use the transverse fields, but then we have to do a number of deflections in transverse fields, both vertical and horizontal, to affect the spin without affecting the orbit. An important concept are resonances, spin resonances. If you accelerate polarized beams in a circular accelerator, they happen when the spin precession is in resonance with orbit frequencies. So a depolarizing resonance is when the number of spin rotations per turn is equal to the number of spin kicks away from the stable direction. And the strength is the number of full spin rotations due to the resonance per turn. So that strength is typically much, much smaller than 1, but it can actually be larger than 1 at high energy. So imperfectional resonances, that's when the spin tune is equal to an integer. And as I mentioned, the spin tune increases with energy linearly, total energy. And so there are many, many imperfection resonances that are being crossed. Intrinsic resonances, when the spin tune is also in a resonance with the vertical betatron oscillation of the orbit, and there, so the vertical betatron tune comes also in the resonance condition. So weak resonances, and the strength is much smaller than 1, they can cause some depolarization. Strong resonances, you can get partial or even complete spin flip. So this is a picture of Alan Krish and Larry Ratner at Brookhaven. And they are in the middle of tuning all the elements that were necessary for the first effort to accelerate polarized protons in the AGS. And that happened during the 80s. And there, the many resonances, both imperfection and intrinsic resonances, were crossed by making them weak, either by making the drive term very small, or the strength very small, or the crossing very fast. And that required adjustment at each crossing of resonance. And you see the scope picture there. Each change there in the upper curve is when you, or each value was adjusted to cross the resonance without losing polarization. The bottom curve shows the crossing of the intrinsic resonance. This was an extremely tedious and at the end really heroic effort to accelerate the polarized protons up to about 20 GeV. By the way, at the time, the polarized proton source that was used for these tests was the atomic beam source based on the Haeberli design we heard about earlier. This effort was so extensive that one had to find a better way to do that, to do it more efficiently and get to higher energies. And to the rescue came the Siberian snakes, which are simply local spin rotators that do not affect the orbit, but just rotate the spin around around a particular direction. This was developed by Durbanev and Kondratenko, both from Novosibirsk. And on the upper picture or schematic, it shows what if you introduce a local spin rotator in a ring where the typical precession axis around the ring is vertical, but that inserted spin rotator rotates around the longitudinal direction, then you can affect the spin tune. It's given by a simple cosine equation, which is shown on the top in the box. And the result of that is that if the spin rotation is not zero, if you have some rotation, then the spin tune can never be an integer, and you eliminate all the imperfection resonances. And we did that in the AGS with a partial Siberian snake. If you make it extreme and make that rotation 180 degrees, then the spin tune becomes 1/2, and maybe even more important, becomes now energy independent. And so by choosing a Betatron tune that's not a half itself, you can avoid all imperfection resonances and all intrinsic resonances. That's usually called the full Siberian snake. And that's what's implemented in RIG. It was actually first tested at the IUCF cooler, of which we heard in the previous talk. So we applied the partial Siberian snake in the AGS I think it was in the 90s. Right now, we actually have 2 strong partial Siberian snakes using a variable pitch helical dipole just to make it compact. Also, we moved the vertical Betatron tune very close to an integer that avoids most of the intrinsic resonances as well. And the result was that we could reach very high polarization up to 70–75% at the full energy of 25 GeV in the AGS. And in picture, you see Haixing Wang and Larry Ratner and myself staring at something. Oops. Okay, so for RIG, we needed more. We needed the full Siberian snakes. In fact, the implementation there was using 2 full Siberian snakes that are shown in that schematic as these yellow or blue boxes with an arrow inside. They have to be located exactly 180 degrees in orbit angle from each other, and that was achieved, as well as, of course, needs rotators to provide longitudinal polarization at the experiments. So quite a bit of hardware had to be installed actually after a rig was completed as a heavy ion collider. What you also see is are the polarimeters. They're up at the top of the ring, both the absolute polarimeter, Tom Weiss talked about that, using a polarized jet, and Yusuf will talk about that in the next talk, as well as relative polarimeters. We call them p-carbon polarimeter, and I will say a few words about that. So the atomic beam source that we used for the initial experiments in the AGS was later replaced by a high intensity source, an OPIS, optically pumped polarized ion source. It started its life actually at KEK and then moved to Triumph and then ended up at Brookhaven together with Anatoly Zelinsky, who's really the master of these sources. The intensity is now quite amazing, very reliable and high polarization. So just a few pictures of what Siberian snakes look like. You've seen the first picture already. That's the warm partial Siberian snake installed in the AGS. It's a helical magnet, a helical dipole magnet with a variable pitch. You see another picture in the middle. It's 2.6 meters long, just fits into one of the straight sections in the AGS. Later, we built a second one, superconducting, which you see at the right side. For Rick, the snakes actually consist of 4 individual helical dipole magnets, each one 2.4 meter long. Each dipole has one full 360-degree twist. And so 4 of these, they're superconducting, go with a maximum field of 4 Tesla. And they can be operated in many different ways. In fact, you can even reverse the current in those dipoles. So you can adapt to potential problems, because when we started this, we didn't really know whether all of this will work. So we wanted to have something very flexible, which throughout the life of Rick became actually very useful. The orbit, of course, has to be restored after they go through this Siberian snake to its original location and angle. And a few words about the polarimeter. Polarimetry, of course, is in many ways the most important piece of instrumentation that we have to have for polarized beams. However, since nobody has produced these high energy polarized beams before, this needed to be developed from scratch as well. So the absolute polarimeter, there will be, Yusuf will give some a talk following this one. The relative polarimeter is based on an internal carbon target. In fact, it uses a carbon target that was developed by Hans Otto Meyer at Indiana for an internal target for the cooler. And we use that really marvelous device. This target is ultra thin, has about 100 monolayers thick, and in our case, it's about 10 microns wide. It's so thin that very slow recoil carbons from a scattering, small angle scattering, can actually leave the target and be detected, and that's the basic principle. So the low angle scattering in the CNI region has very high cross section, significant analyzing power, not very big but significant, which gives a very good figure of merit for this. So fast measurements are possible, and as already mentioned, recoil carbons can be detected with silicon detectors. The target itself is so thin, but has a large surface area because it's a ribbon, that it can be radiation cooled. And we push it to the almost breaking point, and it can only survive with radiation cooling. And it can measure, because it's a thin target, it can measure both horizontal and vertical polarization profiles, which turned out to be very important for INRIC to have this information. And it leads to very negligible emittance scores per measurement. A fantastic device, really. So the bottom line is we reached 255 GeV, about close to 60% polarization. As you can see in the measurements, the multiple measurements were done with the p-carbon polarimeter throughout the store, and the polarization drops a little bit. So there is some polarization loss during the store, but it's not very much. And luminosity was also very high. Now, just a word about the future. So the future for RIC, of course, is the electron-ion collider. And for the electron-ion collider, only one of the two RIC rings will be used as the hadron ring. So it's one of the RIC rings. In this case, we can then go to 6 Siberian snakes. Using more than 2 Siberian snakes makes the spin dynamics more stable. So this loss during the store can be reduced, and also maybe somewhat more polarization could be achieved doing acceleration. But maybe more importantly, it will allow the acceleration of polarized helium-3 in RIC. Helium-3 has a higher magnetic moment, and so all the resonances are stronger, so it will need more Siberian snakes. If one wants to go to even higher energies, maybe at another machine, one could use more and more Siberian snakes. And it turns out that one could extend that to a few TeV. At that point, the precision alignment becomes so extreme that it's probably not possible to accelerate polarized protons to even higher energies. Electron-ion collider, of course, has also electrons, needs electrons, polarized electrons. And so the acceleration of polarized electrons to the 18 GeV energy uses quite a novel scheme for electrons. Namely, it uses a rapid cycling synchrotron with very high symmetry, and that will suppress the strength of the intrinsic resonances up to these energy. So this is quite novel, but in a way it's very similar to the first attempt of accelerating polarized protons in the AGS that I've showed you pictures of. Just as for a comparison, of course, accelerating polarized electrons is quite possible in a LINAC. For example, the recirculating LINAC accelerator at CBAF can very well accelerate fully polarized electrons to 12 GeV, and this could be extended to 18 GeV as well, but EIC has chosen this novel method. And just I want to point a little bit into the future, further future, and maybe for some entertainment. I want to introduce a new concept that we developed a few years ago, a new concept that would allow to collide potentially fully polarized electrons and positrons up to 300 GeV beam energy in a 100-kilometer ring, something that is planned for at CERN for the FCC EE. It consists of a multi-turn energy recovery LINAC, actually 2 of them, that accelerate beams from an injection energy to full energy, collide, and then recovers all the energy by decelerating the beams back. In order to recover the initial emittance of the beams again, there would be damping rings in our scheme. There would be 2 GeV damping rings that you see there in the schematic, both one for the electrons and one for the positrons, where the luminosity would be damped down. Therefore, the emittance would be damped down again because emittance will be blown up during the collision process. It turns out that at the same time as the emittance is reduced, the polarization actually starts to build up from the circle of turn-off effect. And since this is a closed system where the beams continuously go from the damping ring to the main accelerators colliding, deceleration, and back into the damping rings, polarization will build up as it builds up in a storage ring. So this scheme would allow for fully polarized electron-positron collisions up to very high energy. So it recycles both energy and polarized particles, both positron and electrons. We thought that's a very interesting new concept. Whether it actually gets implemented, we'll see. So for the rest of the talk, I just want to say a few words about the parity violation experiments at SIN, now called Paul Scherrer Institute, PSI, as viewed by a graduate student. That was my graduate student, my PhD thesis experiment. You can see that all the people that were participating in this experiment, and Willy Haeberli was a very important participant in that experiment, and it was the first time I met Willy actually. So the experiment was actually initiated and led by Marcus Simonius from ETH Zurich. He was a theorist, but he turned out to be also an exceptional experimentalist, I must say. And Willy Haeberli, that's my impression, clearly knew how to do experiments. That was the impression I got from being in that group. And I was the second graduate student on the experiment. All 3 of these were from Basel, Switzerland. I don't know what that really means, but I do know that Basel was an important place for spin physics all along. So the experiment was about measuring parity violation in low energy nucleon-nucleon scattering to extract the weak meson-nucleon coupling constants. So there are coupling constants for the pion, the rho, and the omega meson. And when that was originally conceived, actually, there wasn't an established Weinberg-Salam theory or weak interaction. And in fact, it was conceived before neutral currents had been observed. So part of the motivation for this experiment was also not just to see whether there is any parity violation in strong interactions, but also to have an additional way to study weak interaction. So the experiment is very simple, and I think that goes back to, I heard that in previous talks that really liked simple experiments. It just measured the difference in the cross-section relative to the helicity of the beam, which meant this was my first contact with polarized beams as well. So you change the helicity of the beam and you measure difference divided by the sum, and that's the longitudinal analyzing power. And you see the results were not 0. So for PP scattering, it's minus 1.5, but 10 to minus 7. So these are extremely small effects. My experiment was the P alpha scattering, and it was 3.3 plus minus 1 approximately. And then one can expand this value into those coupling constants. And you see that the PP scattering is not sensitive to the pion coupling constant, but the alpha, P alpha experiment is. And so using these 2 experiments, it's possible to extract some of the coupling constants approximately, and you still have maybe you need maybe 2 more experiments than just these 2. So the experiment was done at SIN using the injector cyclotron, and the arrow first shows where it was originally located, and while I was part of the group, it was moved to a new hall, and I understood that Willy was actually instrumental in getting this new hall built, called the Haeberli Hall, where the second phase of the experiment was installed. Because of its very high precision, it needed enormous amounts of events, 10 or 16 events. So it had to be an integrating detector. You couldn't really count individual events, with all its challenges that come along. At these very low energies, scattering is preferred to transmission. Other experiments use transmission at higher energies, because the thick targets that you need would really cause too much effect on the beam and cause systematic errors. The target, nevertheless, was pretty thick target. It was 100 atmosphere circulating gas target to maximize the scattering, and the gas was circulated to minimize thermal effects. And it still amazes me that this ever worked, because 100 atmosphere is not easy to handle, and it was separated by a thin aluminum window from the beam vacuum. So we never had a break of that, but it was exciting. And the scattering angle and energy were defined by the scattering, the target vessel wall. And I was a young physicist at the time, and so I didn't really know how you would extract this, but Willy was making these plots where he was able to put the results of the various experiments, in this case the PP, which is the horizontal bar, and the P alpha, which is sort of diagonal line, and use that to determine in a simple way what the possible range of those coupling constants could be. I remember I was very impressed by that.
Tom, are you close to a conclusion?
Yes, I am. So a summary. So clearly Willy Haeberli made many contributions to spin physics and fundamental symmetries. He was one of the greats in spin physics, who recently actually passed away. Unfortunately, as is Ernest Courant, who passed away in 2020, and Alan Krish passed away also in 2020. Willy was also a long-term member of the International Spin Physics Committee. And on a personal note, Willy was an important collaborator on my thesis experiment, as I explained, and he was very, very generously advised and mentored me and gave me sage advice for my career here in the United States. Thank you.
Thank you very much, Tom, for a very interesting talk. I'm sure there will be questions. Yes, Steve.
Hi, it's Steve Vigdor. Hi, Thomas.
Hi, Steve.
On this very interesting idea that you had for the polarized electron, polarized positron collider, are you putting together a group of interested experimentalists to think about the measurements one does with that?
Well, so we, of course, first thing we did, what is it now, 3 years ago or so, we talked to the CERN guys that work on FCCE, because we thought that might be a good alternative to their design, which was a storage ring. And so they were interested, and in fact, it reached to the level that the CERN DG decided to establish a committee to look at this. Not just this, there are other ERL proposals. You know, it could be done even better if you have just a linear collider, right? Because the energy is still limited by the fact that you have to bend the beams. And so that called the lab director group, I think. They reviewed it and they thought it could work. It's also, of course, part of the SNOMAS process this year. You know, this is not a 100-kilometer long accelerators are not cheap things. So, but yes, it's in the process. It's being discussed. It's being considered.
Other questions? Okay, if not, I'm going to use the extra minute to tell those of you that haven't heard yet, and they were not yesterday at the memorial, that this is the book of recipes that Willy wrote, at least 95% of it, and it was concluded by Willy Haeberli mostly, and in part also by his daughter, Willy Haeberli. And there are quite a few copies out here, and there will be more for dinner if you want. So in case there aren't enough right now, just let me know how many more you want, and they'll be delivered for dinner. Thank you.